we want to solve the system 5x plus 8y equals 9 and 2x minus 7y equals 13 using matrices. I will point out, you could totally solve this relatively not terrible system of two equations and two unknowns just by like multiplying one equation by something and adding it to the other one and eliminating a variable and then solving and plugging back in. But that's not how they want us to solve this. They want us to write it as a matrix equation. So first write it as a matrix equation. A times X equal to B. So our matrix A, again, A is always the coefficient matrix. So A is going to be the matrix 5, 8, 2, negative 7. X is your variable vector, x1, x2, or xy, whatever you feel like writing, or whatever variables have been used. I should really have written xy, not x1, x2, because my variables are x and y. So I should change that to x and y. Sorry about that. And then it's going to equal 913. So all we've done is rewritten this equation as a matrix equation. Now, the solution to AX equals B is X equal to A inverse times B. And the work that we're not showing, but that you could show if you wanted to, right, is that if you take this equation, A times X equal to B, and multiply both sides on the left by the inverse of A inverse times A times X equals A inverse times B. What's special about A inverse times A? Or what do you get when you multiply A inverse times A? Right, you get the identity matrix. And then the thing that's special about the identity matrix is the identity matrix times anything is just the anything. The identity matrix times X is just X. So you've got X equal to whatever A inverse times B is. Now this only works if A is invertible. So we're going to find the inverse, but we're going to check to see if we can find it in the process. So A inverse is equal to 1 over the determinant of A. Well, the determinant of A is going to be 5 times negative 7 minus 8 times 2. I don't know what that is yet, but I'm pretty sure it's not 0. So I'm pretty safe here. The determinant is not 0. We're good to go. Oh, yeah. Determinant of A is not equal to 0. That means A is invertible. Times, okay, you just have to remember this next part. For inverting A, you're going to take the diagonal things and switch their places. So 5 and negative 7 switch spots. So you've got negative 7 and 5. We switch them. And then the off diagonals, you change their signs. So you change anything positive to negative, anything negative to positive. So 8 becomes negative 8, 2 becomes negative 2. That is always the process for a 2 by 2 matrix, every time. And then I would probably simplify this denominator. 5 times negative 7 is negative 35. Negative 35 minus 16 is negative 51. You get negative 1 over 51 times negative 7, negative 8, negative 2, 5. There's your A inverse. Oh, there's something in the chat. Sorry, I didn't see that there. You got too many papers. Sorry, I'll have the papers over here. 1 second. I'm trying to see the chat. Oh. Oh. Oh, okay, cool. All right, cool. No worries. Thanks. Good to know. So we're not quite done though, because we have to do X equal to A inverse multiplied by B. So we're going to say that X is equal to this matrix, negative 151. You could distribute the negative 151 to each of the terms in there. I wouldn't, unless it happened to be like, if it was maybe like negative 2, then I might distribute it because the thing that we're not going to get gross fractions in it. But like if it's going to be all fractions, just leave it out in front. So we got X equal to that matrix multiplied by B. And I picked gross numbers on purpose, but things are going to get kind of gross here. So let's figure out what we've got. So we've got -1 over 51 times -7 times 9 is -63. And -8 times 13 is 80 plus 24 is 104. So -104. And I should be super clear here. That is -63 minus 104, right? I'm not getting a 2 by 2 matrix. I'm getting a 2 by 1 matrix. So there's only one column. So I need to subtract these things still. And then in the bottom row, I get -3 times 9, and then plus 5 times 13, which is 65. So simplifying a little bit more, I get -1 over 51 times -63 minus 104 is -167. And -18 plus 65 is what? 47. And then if you really, really want to, you can distribute the -151, -150 first and say that's going to be 167 over 51 and -47 over 51. And that is what your X and your Y are that solve this equation. They're not nice. We could have totally solved this probably with less work a different way. But this is generally the way they're going to ask you to solve an equation like this if they ask you to do a thing like this. Hey, come on. All right. A number of people asked me about, oh God, what are the words? I don't remember the words. The dynamical system thing. I know what the process is. That particular name doesn't ring a bell to me. So what I'll say is the next couple examples are probably more geared towards the people in Goldsmith's class. That doesn't mean they're bad to see. If you're going to be in 17C, this kind of thing is going to show up anyway. And I suppose it's possible that Lee goes over this. I doubt Alvarado will get to this. So we'll talk about it. It still involves a lot of the same processes that we've already talked about. So it's worth paying attention to, even if you're not in Goldsmith's class. So we're going to show, we'll start small. Let's show that the matrix A is equal to some P times some D times some P inverse, which we'll talk about in a second, for A equal to the matrix 1, 2, 2, 1. So first of all, let me talk about what P and P inverse are. So P is the 2 by 2 matrix whose columns are the eigenvectors of A. P inverse is P inverse. If you know what P is, then you know what P inverse is. You just find it the way we just found A inverse. So P inverse is the inverse of P. That seems kind of dumb to write, but since we're talking about what all things are, fine. And then the matrix D is a diagonal matrix. What do I mean when I say diagonal matrix? Well, let me ask you all. Is that matrix there a diagonal matrix? Good question, is it? It is not a diagonal matrix. It's not a diagonal matrix because it has entries on the not diagonal that are not 0. So to be a diagonal matrix, all of the non-diagonal entries have to be 0. So here are some examples of diagonal matrices. Whoops, that's not good job, James. There's a diagonal matrix, 1, 0, 0, 3. Here's a diagonal matrix, 2, 0, 0, 0, 5, 0, 0, 0, 1. Here is technically a diagonal matrix. As long as the off diagonal entries are all 0, then the matrix is diagonal. And technically, the diagonal entries could also be 0. It's just kind of boring if they are. So diagonal matrix just has zeros on the off diagonals. Now, D is extra special here. It's a diagonal matrix whose entries are the eigenvalues of A. And to be even more specific, I'm not going to write this down, we'll just say it. The order that the eigenvalues go in is the same order that the eigenvectors go in as columns of P. So for example, if our eigenvalues are lambda 1 and lambda 2, and the eigenvectors are v1 and v2, V1 obviously being the eigenvector for lambda 1, V2 being the eigenvector for lambda 2, then the matrix D could be lambda 1, 0, 0, lambda 2, but then the matrix P would have to be the first eigenvector in the first column, the second eigenvector in the second column. But you could change the order if you wanted to. You could alternatively do it as D equal to lambda 2, 0, 0, lambda 1, and P equal to, then V2 would have to be first, V1 would have to be second. So the order that the eigenvalues go in has to match the order that the eigenvectors go in your P and D matrices respectively. Cool. All right, so now we've talked about what all the things are. Let's go ahead and find them. And sometimes, well, so this is where our practice finding eigenvalues and eigenvectors is going to be super important. So here's our matrix A again. It's 1, 2, 2, 1. I want you to find the eigenvalues. They are nice integer values. I'll give you 2 whole minutes. Awesome. All right, hopefully you're getting 3 and -1. Well, let's check and see what we've got. You multiply this out, I've got a 1 minus a lambda. Wow, that's a lambda, James. Okay. Wow, my lambda there is suspect. Minus another lambda plus a lambda squared minus 4. Rewriting this, I've got lambda squared minus 2 lambda. 1 minus 4 is -3. And then this does factor as lambda minus 3 times lambda plus 1. So we're getting lambda 1 equal to 3, lambda 2 equal to 1, -1, sorry. The choice of which one is lambda 1 and which one is lambda 2 is totally arbitrary. Sometimes some books make a distinction that the first one should be the one that's like larger and positive if there is a positive one, but it doesn't really matter. Okay, let's find the eigenvectors. Eigenvectors. So let's start with lambda 1 equal to 3. Has anyone's teachers expressed a preference for which way you do this? Meaning, have they said you need to do it as A times V equal to lambda times V, or have they said you need to do it as A minus lambda I times V equals the 0 vector? The second one, okay, that's pretty typical. It's not my favorite way, but we can do it that way because it's not terrible. So doing it that way. So here's what I would recommend. When you're doing it this way, I definitely recommend looking back at the thing you've written right here. and just putting your value of lambda in for lambda there. So for lambda equal to 3, I'm just going to look at that matrix and say, okay, I've got 1 minus 3, 2, 2, 1 minus 3 times my eigenvector equal to 0. 0 is what I should really write. Right, that's what this is right here. That's your A minus lambda. So, right, just to be extra clear here, right, this matrix is your A minus lambda I. This is your eigenvector you're trying to find. That is obviously your 0 vector. Pick either row you like. They should virtually be the same. I'm going to pick the first row. So negative 2x plus 2y equals 0. That gives me 2y equals 2x, or just good old y equals x. All right, I want everybody to write down the eigenvector that you know I would write down if I was picking an eigenvector. You get to pick. You get to pick anything you want, but you're going to make the James choice. All right, you got 10 more seconds to write down a couple numbers. All right, time's up. Here's my choice. 1, 1. If x is 1, then y is 1. You could have picked 2, 2. You could have picked 3, 3. You could have picked negative 7, negative 7. You couldn't have picked what? Thank you. 0, 0. Right? No, you can't have 2 zeros. You can have 1, 0 if that works. It wouldn't work here. So there's our eigenvector. Let's find the other one. So for lambda equals negative 1, we'll do the same thing. I'm just going to look at this matrix here and plug in negative 1 for all my lambdas. 1 minus negative 1 is 2. 2. 2. 1 minus negative 1 is 2. Times xy equals 0, 0. So that means we get 2x plus 2y equals 0. We get 2y equals negative 2x, or just y equals negative x. So here are my eigenvector. There's probably 2 standard choices here. You could pick 1, negative 1, or negative 1, 1. Either way, it's fine. I'm going to go with 1, negative 1. I think it's usually more typical to make x positive and y negative if they're opposite signs. And I should say this is my v1 here. This is my v2 here. That's my lambda 2, my lambda 1. All right. Questions about anything we've done so far before we start building up P and P inverse?
Does that like what about V1, V2 like our eigenvector?
So yes, V1 and V2 are the eigenvectors for lambda 1 and lambda 2. So specifically, V1 is the eigenvector for lambda 1 equal to 3. V2 is the eigenvector for lambda 2 equal to negative. Yeah. Correct. Yes, that is the first step to hold this whole, what's it called again? The dynamical what? The dynamical time system. Yes. Because so here's what we're trying to build towards. We're trying to build towards starting with some initial condition and then saying, what happens if you multiply this initial condition by this matrix repeatedly? Because essentially, and we'll do a more like wordy example in a minute here, where you're actually like saying like, okay, we're starting with like juveniles and adults, and like something happens every time iteration. You get some percentage of them becoming adult and some of them dying, whatever. And the matrix tells you how many of them live and how many die. And so then if you want to keep seeing, well, what happens 20 years from now, you have to keep multiplying by the same matrix. And the problem is multiplying by a matrix repeatedly is a lot of terrible work. And this is a way of shortcutting it to make it much easier. It's not always possible. It will be in this class, but I was pointing out, this process is not always possible because not every matrix can be written this way. Because not every matrix has the right number of eigenvalues and eigenvectors. But that's not really a topic for this class, so we don't need to talk about that. All right, so let's go ahead and write P. And I'm just going to pick P to be the vector where the matrix, sorry, where this is my first column. So P is going to be the matrix where V1 is the first column. And when you're writing a vector in a column, you write the vector and then you write like little dashes above and below it to indicate like it's the whole column. I don't really know why, but it is what we do. And so P is going to be the matrix 1, 1, 1, negative 1 as our, and I know I said that kind of backwards because I would say I usually read rows, not columns, but those were the columns that I was reading. Okay. And then let's find P inverse. The P inverse, again, we're going to do the usual thing to find P inverse. We're going to find the determinant of the matrix that we're inverting. Just gonna be 1 over -1 minus 1 times, okay, this one's gonna look a little weird because it's gonna feel kind of the same. You interchange 1 and -1, so you get -1 and 1, and you change those to the opposite sign, so you get a -1 and a -1. And here I probably would distribute the -1 half that's out in front. So I'm gonna get a 1/2, 1/2, 1/2, -1/2. There's P inverse. Right, because this here is a 1 over -2. And finally, D should just be the diagonal matrix with a lambda1 there and a lambda2 there, which is the matrix. Let's see, lambda1 we said was 3, 0, 0, -1. It is possible that two of you could do the same problem and get different P's and D's because someone else might make the choice where V2 was the first eigenvector and V1 was the second eigenvector, and then their D would differ slightly. It's like taking a different path to get to the same answer. You're still going to get to the same answer. All right, so here's what we've been working towards. We now get to say that, sorry, what do we say? That the matrix A is equal to P times D times P inverse. Normally we wouldn't check this, but we're going to check it here to make sure that it's really working. So we can, oh yeah, we're convinced. So I forgot what A was. So A was the matrix 1, 2, 2, 1, and we're hoping that's equal to P times D times P inverse. So here's P, 1, 1, 1, -1. There's D, 3, 0, 0, -1. There's P inverse, 1/2, 1/2, 1/2, -1. The bummer about multiplying three matrices together is you have to just pick two to work with first. You don't have it. There's no way of doing all three at once. So pick two. I'm going to pick these first two here. So that's going to equal, all right, let's see here. So 1, 1 dotted with 3, 0 is going to give me 3. 1, 1 dotted with 0, -1 is going to give me -1. 1, -1 dotted with 3, 0 is going to give me 3. 1, -1 dotted with 0, -1 is going to be +1. And I still have to multiply by that. And now things are going to get a little bit messier. So now 3 times 1/2 plus -1 times 1/2 is 3 halves minus 1/2, which is 2 halves. 3 times 1/2 minus 1 times minus 1/2 is 3 halves plus 1/2, which is 4 halves. 3 times 1/2 plus 1 times 1/2 is 3 halves plus 1/2, which is 4 halves. And 3 times 1/2 minus 1/2 is 3 halves minus 1/2, which is 2 halves. Check. It's the matrix we said it should equal. So why is this useful? Well, here's why it's useful. And your teacher, well, some of your teachers may have talked about this, they may not have. The point here is that now I can raise A to any power, and it's not that hard. So someone might ask you, what's A to the 20th power? Okay, that seems terrible. I don't want to do A times A times A 20 times. So I'm going to rewrite it like this. I'm going to write it as P times D times P inverse to the 20th power. Okay, check this out. This is where I think the interesting thing happens. When you actually multiply this out, you get P times D times P inverse times P times D times P inverse a bunch of times, 20 times to be exact. But look what happens in each of the middle parts. The P inverse here times the, sorry, you can't see that P there very well. The P inverse here times the P there is what? Yeah, they're the identity. They cancel out. They become one essentially. And the P inverse here times the P that would be there is also the identity. And all the P inverse times P's in the middle of this expression just become the identity matrix. So what you're left with is just P out in front times D 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 20 times P inverse. Which still might not seem better until you learn that a diagonal matrix raised to a power is really, really nice. So just as a quick aside over here, d squared is 3, 0, 0, -1 times 3, 0, 0, -1. But look, when you multiply this out, you get 3 times 3 plus 0 times 0. You get 3 times 0 plus 0 times -1, which is 0. You get 0, -1 times 3 dotted with 3, 0, which is also 0. And you get 0, -1 dotted with 0, -1, which is -1 times -1. When you square a diagonal matrix or when you raise a diagonal matrix to any power, you just raise the diagonal entries to that power. Always. So here we could say that d to the 20th power is going to be 3 to the 20th, 0, 0, -1 to the 20th. I don't know what 3 to the 20th is, and I'm not going to try to find it, but I know that -1 to the 20th is just 1. So we could totally write this as the matrix P, which is 1, 1, 1, -1, times this matrix we just found over here, 3 to the 20th, 0, 0, 1, times P inverse, which was, where'd you go P inverse? 1/2, 1/2, 1/2, -1/2. Which still looks kind of gross, but it's definitely a way of multiplying a matrix to a higher, or taking a matrix raised to a very high power relatively quickly. I guess we could multiplying this out seems silly. You could, I guess we should. So I would multiply these two matrices together. 1 times 3 to the 20th plus 0. Get 3 to the 20th. And then that times that gives me a 1. And then that times that gives me a 3 to the 20th. And then that times that gives me a -1. So I have to multiply this by 1/2, 1/2, 1/2, -1/2. This is the last part where things are going to get kind of silly. 3 to the 20th times 1/2 plus 1/2. I would write that as 3 to the 20th plus 1 all over 2. And I know things are kind of super scrunched in there. Let me zoom in so you can see a little bit better. That's 3 to the 20th plus 1 over 2. And then that times that is 3 to the 20th minus 1 over 2. And that is also 3 to the 20th minus 1 over 2. And that is 3 to the 20th plus 1 all over 2. Sorry, that's not my best work ever there. Let's do a question that has more of a real world vibe to it. Yeah, sure. Let's look at this example here, which is kind of interesting. Or I should say, are there questions about anything we've done before we move on to another example? All right, let's look at an example with populations of things. 3, 2, numbers. Who needs numbers? Suppose we are studying the population divided into 2 age classes: juveniles and adults. Juveniles have an average of 2 offspring, while adults have an average of 6. %50 of juveniles move on to become adults. Of juveniles move on to become adults. And adults don't move on to become adults. Adults just die. There's often like usually the oldest age group, either some percentage of them survive to continue being that, or they just say they all like go away. So let's write the matrix to describe this. And I'll use words that you might not, you've heard me say, but I'll just say the Leslie matrix to describe this is the following. 2, 6, 1/2, 0. Here's why that's the case, right? If we think about this multiplying by the number of juveniles at time t and the number of adults at time t. Well, let's see. So watch this here. I'm going to get 2 times the number of juveniles plus 6 times the number of adults. So the new juveniles, the new offspring, I'm going to have 2 times the number of juveniles because each juvenile on average produces 2 offspring. I'm going to have 6 times the number of adults because the same reason, right? Each adult on average produces 6 offspring. So however many adults there were, I have 6 times that number of offspring. However many juveniles there were, I have 2 times that number of offspring. And then in the second row here, I'm going to get 1/2 times the number of juveniles because half of the juveniles survive to adulthood. And I'm going to get 0 adults because all the adults die. I guess. That's what the matrix means. You also could have drawn that picture that we drew last class where you have like A and J and say, okay, well, from A to J, well, let's see, each adult produces 6 juveniles. And each juvenile, half of them make it to adulthood. And also each juvenile produces 2 new juveniles. This is the diagram that would have led to this matrix, which I don't love, but it's fine. Okay, so the question we want to ask eventually is like, what's going to happen to this population of adults and juveniles? Are they going to keep growing? Are they going to die out? What's going to happen? So, like, what might happen after 10 iterations or 20 iterations of this process? Well, to answer that question, we also need one more thing, actually. We need initially. So let's say initially we have 20 juveniles. Sorry, no, that's wrong. Sorry, 100 juveniles. 100 juveniles. And 80 adults. Let's, and that's, we're going to say that at time 0. So at time equal to 0, we have J of 0 and A of 0 equal to 180. How many juveniles and adults do we have after, let's say the units of time are 1 year. Let's say 1 year later, how many juveniles and adults do we have? Well, we know that we should have, each juvenile should produce 2 more juveniles. So I should have 200 juveniles from there. Each adult should produce 6. So I should have 480 from there. So I should have 200 plus 480. That's, wow, how am I doing the math in my head? Why do I just write out the matrix? Right, so the number of juveniles at time 1 and the number of adults at time 1 is going to equal the matrix that tells us how to get from 1 year to the next year. 2, 6, 1/2, 0 times how many we had at time 0. Let's take a look and see what we get. 2 times 100 plus 6 times 80, just like I was saying, which is 680. And then 1/2 times 100 plus 0 times 80. So we get 680 juveniles and 50 adults. And then we could do it again. I can say, okay, well, what about time equals 2? Well, I can take the amount I have at time equals 1 and multiply by the same iteration of the matrix. So I'm going to have now 2, 6, 1/2, 0 times 680, 50. Let's see what we get here. So 2 times 680 is kind of a big number. It's what, 1360, I think. Plus 650 is 300, so I get 1660. Let's double check that. Yep, I do. And then 1/2 times 680 is 340. And the process goes on, right? We can keep doing this and find out, but I want to know, like, so if I ask, what do we have in 20 years later? It's really tedious to keep doing this 18 more times. That's not the point. The point is to do the other thing we were just doing. Saying instead of doing this 18 times, we're going to figure out how to raise this matrix to the 20th power and then multiply it by this vector here. And there's actually kind of two distinct ways of doing this. We'll talk about the one way because I don't think I have enough time to talk both ways. But if we have enough time, we'll talk about the other way. So I really want to know. I need to leave this up here. Look at it. We want to know what J of 20 and A of 20 looks like. All right, so things in order here. In order is, yeah, maybe not. Yeah. Okay. Well, we're going to find the same thing we did last time, right? We're going to find the eigenvalues, the eigenvectors of A. We're going to find P, P inverse, and D, and then we're going to take that to the 20th power. So here's our matrix A again. Was 2, 6 or 6, 2? 2, 6. 2, 6, 1/2, 0. It's a long process, right? So when you see a problem like this, just in general, you should mentally prepare yourself. Okay, there's a lot of steps here. Eigenvalues, eigenvectors, P, P inverse, D, and then use all that to find the thing you're looking for. Let's see how quickly we can do it here. So, eigenvalues. They are not 2 and 0, right? It's, I don't have the nice trick thing I would love to be able to use here, right? I don't have an upper or lower triangular matrix. So I'm just going to say determinant of A minus lambda I equal to 0, product there. So you get 2 minus lambda times negative lambda minus 6 times 1/2 equal to 0. I get lambda squared minus 2 lambda minus 3 equal to 0. I think I have the same eigenvalues as before. Sometimes that happens. I get lambda equal to 3 and lambda equal to -1. Let's call that lambda 1. Let's call that lambda 2. Eigenvectors. All right, I'll do it the way you all like. No, I shouldn't say you like it. It's a perfectly good way. It's just not my preference, but it really is a fine way of doing it. I should not trash talk it because it is a good way of doing it. And actually, as we saw last class, sometimes it is the better way. When your eigenvalues are gross, doing it the way you all are doing it, or probably doing it, is probably the better way. So I should really emphasize you should do it that way. It is probably generally the better way, especially if you're going to take 17C next quarter. So yeah, I should get used to doing it the other way is really the truth here. Anyway, eigenvalues lambda 1 equal to 3. And then I don't know about that. So 2 minus 3 is -1, 6, 1/2, and 0 minus 3 is -3 times my, you can say XY or JA. I'm just going to use XY, even though I know I've got J and A equal to 0, 0. I would definitely use the first row, -1 times X plus 6 times Y equals 0. So 6Y equals 1 times X. So pick your eigenvector to be somebody tell me. Thank you, 6, 1. Right, X is the coefficient of Y, Y is the coefficient of X. That's the nice, fast way of seeing it. All right, let's find the other one. Lambda 2 equal to -1. Let's see, so plugging that in, we're going to get 2 minus -1, 6, 1/2, and 0 minus -1. Again, I'm always going to try to use the integers versus the fractions if I have a choice, because it's easier for me typically. So I'm going to say 3 times X plus 6 times Y equals 0. 6Y equals -3X. I would divide both sides by 3. I don't want to introduce fractions, but I do want smaller integers if I can help it. So I'm going to have 2Y equal to -X. So then X gets to be 2, Y gets to be -1. Cool. Then we find P. So P is just take that vector and that vector and write them as columns. 6, 1, 2, -1. We can also write down D as well. So be careful, right? If that's V1 and that's V2, then our D is going to be lambda 1 has to go first. And lambda 1 was 3. So there's our lambda 1 in the first column, lambda 2 in the second column. And then P inverse, we have to calculate. It's going to be 1 over -6 minus 2 is -8. And then we're taking this matrix and interchanging -1 and 6, and then changing the signs of 2 and -1. Cool. So then we have all the stuff we need. In fact, let me back up just a little bit so I can point out that, sorry, in the work we were doing before, I should have pointed out one other thing here, right? When I'm trying to find like J of 1, A of 1, it really is A to the first times J of 0, A of 0. And this here really is A times it again. So when I'm finding, sorry, I got a little ahead of myself over here. J of 2, A of 2 really is A times J of 0, A of 0. Or in other words, it's A squared times J of 0, A of 0. So I'm trying to find the 20th iteration of this. It's going to be A raised to the 20th power. So if I want to find how many adults and juveniles I have after 20 years, it's going to equal A to the 20th power times my initial conditions, J of 0, A of 0. And this is something we are totally capable of doing. The numbers are still going to be large and gross because they are, but here's what's going to happen. We're going to get, well, A to the 20th is really going to be P times D to the 20th times P inverse. So when I try and find this, when I try and find J of 20, A of 20, it's going to be A to the 20th, which is that. So P 6, 2, 1, -1. D to the 20th, which sure we can write the wrong way at first, times P inverse, which is -1, -2, -1, 6. And I'll put the -1/8 out here just because I didn't write it in front. Doesn't matter which side you multiply it on. And then finally, times your initial conditions, which were 180. It still looks like it's a super gross calculation, but it's not quite as gross as it was before. I should say, it is significantly less gross than it was before. This might look terrible, but it's not that bad. I don't think we should actually do this multiplication out because there's not a lot of point in seeing that. It's really just I do get some large numbers times it. Okay. So we have time for another one? Not really. These problems take so long is the problem. Let's talk about the rest of this week. Or actually, I should say, are there questions about what we've said about these dynamical systems? That's a word. Are there questions about what we've said so far? I know it's not the most exciting material, but it does come up. I will say there is another way of doing it that is a little bit different, but is mostly the same. No, it feels very different to me, which we could talk about. We don't have to. Yeah.
So like when we do solve this out and we make it, when we do everything except like 20 power one. What's that last step?
Well, so it would be really like multiplying this out. So the problem is this is always going to look kind of gnarly because you've got large things in here. But if we start multiplying this out, so I've got, let's do a little simplification here. I'm going to remind myself that this is really just 3 to the 20th, 0, 0, -1. Sorry, -1 to the 20th, which is +1. So when I multiply this matrix by that matrix, I do get 6 times 3 to the 20th plus 0. And I do get 6 times 0 plus 2 times 1. Not plus, it's just 2. And then I get 1 times 3 to the 20th. And then I do get -1 times 1. When I do this multiplication here, -1 times 100 plus -2 times 80 is -100 plus 160 is 260, right? It's a lot of like multiplying out and negative that. Okay, -100 plus 480 is 380 times a -1/8 And then we have to multiply this by that. So it's usually we don't get to this step because we are asked to stop somewhere else before, or someone has made a better matrix where like the eigenvalues are like 1 and -1. So when you raise them to the 20th power, it's not terrible. You just get 1 and 1. But here you would multiply this out, and this is where it gets particularly gross, right? You can have 6 times this times -260. Ugh. I feel like my negative here feels. Oh no, there's a negative there. Okay, I was like, that seems like it's gonna be a problem. But it's not. Yeah. So I really don't want to do it, but I will. 6 times 3 to the 20th times -260. Yeah. Plus 2 times 380. And then the second row is going to be 3 to the 20th times -260. Right? Gross numbers. -1 times 380. All times -1/8. And so this top part here is how many juveniles you have after 20 years. And this top part, or this bottom part here, multiplied by -1/8 is how many adults you'd have after 20 years. Number of juveniles, number of adults. Right. So if you are doing this in your class, you definitely should practice it. It's not impossible. And I should say, you should practice the part where you're finding P and D and P inverse. This last step here where I'm multiplying all this stuff out because I picked some arbitrary number to raise it to the power is just trying to show you why you might use this, but it's not typically what you're gonna have to do, at least by hand. But you should definitely practice finding P and P inverse and D, which means you have to practice finding eigenvalues and eigenvectors, and then finding P and D and P inverse. The other thing I want to say is, so we have 2 more days of class. You all have finals next week. What do we want to spend our last 2 days doing? Do we just want to kind of do a general review of the next 2 days? Do we want to talk more about eigenvalues and eigenvectors? And instead of having you all tell me what you want to do right now, I know some of you wrote like things in Canvas for the reflection, which I appreciate. We'll take that into account. But if any of you want to like email me, be like, James, I really love we talked about this or talked about this or this. I'm happy to cover whatever, happy to focus on stuff. I also can just come and do whatever I want because I have lots of things I could talk about. But if there are specific things you want me to talk about on Wednesday and on Friday, I'm happy to try to cater to your needs. Those of you who speak up will get what you want. If you don't say anything, don't expect to get what you want. It's pretty typical. All right, that's all I got for today. Have a lovely rest of your day, and I'll see you all on Wednesday. Or sooner. Eigenvector. Oh, you're talking about like problem 6C? So yeah, so actually, so let me make up a different example. Let's say we had something like, and we should click here. Let's say we had a matrix that was something like, so let me pick my favorite example here. Trace needs to be 5 times 6. Sure, we can go 1, 4, that is 5, 6, that would be 4 minus 2. Let's do -6. Let's do 4 minus 10. That should work out. Let's make this all like 1/3. Let's say that was our matrix. We want to find the eigenvalues. You should ask this question in class. It would be good for everyone to see. But so if we're going to find the eigenvalues here, it's going to be the determinant of 1/3 minus lambda, 2/3, 5/3, 4/3 minus lambda. 4/3 kind of looks like a lambda there. Okay. And then if we take the determinant here, it's going to be, you come on in. I'm just 1/3 minus lambda times 4/3 minus lambda minus 2/3 times 5/3 equal to 0. Multiplying this out kind of sucks. What I, come on in. What I would say here is that, what you can really do is you can multiply both sides by 3 twice. If you multiply the entire thing by 9. Well, take a look. So one of the 3's here gets to go here. One of the 3's gets to go here. So what I'm gonna end up with is 3 minus 3, or sorry, 3 times 1/3 minus 3 lambda. And 3 times 4/3 minus 3 lambda. Minus 3 times 2/3 is 2. 3 times 5/3 is 5. I'm not saying it's a whole lot better, but at least now you're dealing with integers. So when you multiply this out, you get 9 lambda squared minus 12 lambda minus 3 lambda is minus 15 lambda plus 4 minus 10 equal to 0. So you've got 9 lambda squared minus 15 lambda minus 6 equal to 0. It's not great, but you can probably still factor this. I would personally divide both sides by 3 first and say I have 3 lambda squared minus 5 lambda minus 2 equal to 0. And I'm pretty sure this factors as, let's see here, I want a minus 2 here and a plus 1 here. So that's a little bit easier way of getting, I mean, easier probably, but like, it's not as terrible. Yeah, you can totally multiply both sides of the equation by whatever number you want. So like the one that's your homework, you could definitely multiply both sides by 13 times 13 to get rid of the 13 squared on the bottom. And you're welcome to this page if you would like it.
Thank you.
You're welcome.